we might as well just get started. Our speaker today is Dr. Pedro Lomonaco. Pedro received his bachelor's in civil engineering from the National University of Mexico in 1991 and a master's in coastal engineering from the International Institute of Hydraulic and Environmental Engineering, Delft, the Netherlands in 1994, and his Ph.D. in civil engineering from the University of Cantabria, Spain in 1999. Dr. Lomonaco is the director of the Hinsdale Wave Research Laboratory at Oregon State University, as well as teaching faculty of ocean engineering and coastal infrastructures for the School of Civil and Construction Engineering. He has over 30 years of experience with academia and industry on theoretical and applied research studies of physical modeling of waves, current and wind structure interactions. He's authored and co-authored more than 100 papers in scientific journals and conference proceedings, and has prepared more than 60 technical reports of national and international projects and studies. The scientific activity primarily deals with studies of physical and numerical modeling of wave generation and propagation, wave structure interaction, stability of coastal and submarine structures, behavior of floating structures, characterization of wave energy converters, offshore wind technology, hydrodynamics, scour protection, and nonlinear behavior of long waves in shallow waters. With that, I'll hand it off to Pedro, and he can get started on his presentation.
Thank you, Hannah. As you can see, my interest goes to everything you can imagine that goes into the water is what I like. Okay, so what I'm gonna present you today is a little bit on the background on how do we do the scaling and what do we have to consider when we are doing the scaling of physical models in the laboratory. So, oh, is it working? There you go. So this is an example of two structures. I have to say they are not exactly the same structure. One is the model, the other one is the prototype. What is interesting that I found in this image is the shape is similar, and also the pieces uses for the protection of that coastal structure is the same. What you see here at the round head is protected with cubipods, which are the same units that are being used here. But here you have the scale of that structure. This is a massive structure, is quite big. You see a person over here, and this is a model scale of a similar structure. Is a groin that is in Brazil. This is in Spain. The prototype is in Spain. This model is a model of an inlet in Brazil. And here you see a number of components and things that are happening between one and the other. But the interesting thing is when you want to build a structure like the one you see on the right, you have to invest a lot of money. It's an extremely complex and massive structure. It's very expensive, and you don't want to make mistakes. So still nowadays, even though numerical modeling is pretty advanced and so on, there are certain things, particularly for extreme events, for example, in this breakwater, that physical modeling is necessary. And that is the reason of what you see around here. So when we are forced to do the physical modeling, and what we have is part of the project to do the physical modeling, then we have to consider how can we do the scaling, how can we do the construction of a model like this that represents properly what's going on over here. And that applies to fundamentally every structure that we build in the ocean or at the coast. So you will see some examples here and there. There is a little bit of mathematical background. I will go relatively fast over there, so you don't get bored. But at the end, the idea is for you to get the fundamental concepts of how we go from the prototype to the model scale. So a little bit of definitions and things that we have to remember. And those are things that I want to highlight. When we talk about a physical model, and in between brackets is they put physical, because sometimes we are talking about numerical models that also can be used for scaling down the processes and represents a phenomena that is in a reduced scale for a number of reasons. But a model is a representation of what we have in the prototype. And prototype, what we mean is the full scale structure. In mechanical engineering, there are other definitions of what is a prototype. Prototype, in our case, what we understand is the full-scale structure or device. Sometimes the model is at a different scale, not necessarily. And sometimes we do these experiments in the field, and sometimes, most of the time, is in the laboratory in a controlled environment. No, so the model is in the laboratory will be subject to hydrodynamic conditions. And again, in between brackets, because I'm gonna talk about hydrodynamics, so waves, currents, water, and so on, but it could be something else. Could be wind, could be electronics, could be whatever is. This is really open to other disciplines, but I'm concentrating in hydrodynamics. Two elements, which is what is the criteria of similitude and what is it, and what are the conditions of similarity. So the similitude is when you have certain physical relationships that are imposed to the similitude is for example, when you have two physical relationships, so current or wave height or dimensions, and when those physical parameters are being acting in the prototype and in the model, when you compare those are similar. They are similar in geometry, they are similar in forces, they are similar in characteristics. So this is the criteria of similitude, that some two things are similar and between the model and the prototype. So which is related to what are the conditions of similarity. So those are the conditions that the experimenter chooses. So we make the physical model reproducing the prototype, so the results are satisfactory. So when we do these things, and we will see how we have what the things that we have to take into account between the in these conditions of similarity, you will see that we cannot do perfect similitude. And there is a number of reasons why, and that's what we're going to be seeing here. And when that happens, then we say that we have scale effects. Because when we are reducing the scale, we cannot reproduce all the physical conditions exactly the same. And we have to just be aware of it. We know just have to know how far we can go with those conditions of reduced scale. And then we know that there are going to be scale effects. It is there, we know exist, but we have a problem. We don't know how much they are. And it's very difficult to assess the scale effects unless we do experiments at different scales of the same thing, or we do measurements in prototype. That is, and that is extremely expensive, or sometimes impossible. So we know that we have scale effects, but quantifying them sometimes is impossible. And there is something different, and we just have to be careful with that. And I will address this at the end very briefly, is what are the laboratory effects? The laboratory effects are not scale effects, are produced by the experimentation that you are actually doing. And we will see that there is sometimes it's easy to mix up what is the scale effect and what is a laboratory effect. But this is more because we don't have the right facility, or the facility is small, or the facility has a certain configuration, or we have something that is affecting our measurements, like instrumentation, that are properly or are produced by the laboratory or the specific design of the model that we are doing. And a final comment, more than definition, is what you have to do, what you have to keep in mind is the design of a model, if it's numerical or physical, requires you to understand what is going on. And that's what I'm saying in the basic underlying physics or theory. You have to understand what's going on. Otherwise, you're just basically trying to do something without knowing what is going to happen. So the first thing to do is to understand that. That's why I do believe that, for example, the similitude running experiments in the lab here, for example, requires us to understand what is a wave, and you will also need to know what is what is a wave. It's important for you to see to picture what the wave is doing to your structure and or devices. So there are three in general. Well, this is this kind of the classical way of addressing this similarity. We have three components of similarity. The first one is the geometric similarity. This is kind of the classical thing. You remember the image of the elements that we were testing, that the pictures of the breakwater that was showing you in Spain and in Brazil. So the model was in Brazil and the prototype in Spain. We were using one of these elements. So this is just an example of a reduced scale. This element is geometrically similar to the one that you saw in the picture. The difference is that that piece that was cubipod is exactly geometrically small. So it's like, imagine that you scale down in the computer. Now you know that you can basically scale down by dragging and creating a reduced scale. This concept is quite simple because it's just a geometrical thing. So this shape is exactly the same as the other in terms of size. The kinematic similarity is when kinematic means velocity, and then is when we are studying the particles, the water particles that are moving, and that motion should be the same. So imagine the streamlines of my current should be the same, and they are similar to what happens in the model to the prototype. If we can draw a vector of the motion of that particle and we scale down geometrically, we should get the same function of that vector moving across the, for example, a flow of water that goes around my structure. And the dynamic similarity is something equivalent to the kinematic similarity, but we instead of talking about the water particles or the water motion or the velocities, we are talking about the forces. So how the forces in prototype are scaled down, and they produce the same relative effect, and that is the definition of dynamic similarity. Geometric similarity is the easiest to achieve because it's just a problem of building things small. Kinematic similarity, it depends on the shapes a little bit and how the flow is produced, so it's relatively easy also to achieve in most of the cases. Dynamic similarity is our main problem. So a little bit of equations. Don't be afraid. I'm not going to go super crazy on this, but I think it's important for you to see. Let me change my things to a powerful laser. So classical approach in fluid dynamics is to treat first with two fundamental equations: the continuity principle, which means that everything that goes in a water particle, let's imagine this is a box of water, everything that goes in minus everything that goes out is equal to the amount of mass or volume of water that stays in that box. It's kind of simple. We do not create or destroy matter. It's either going in and out, and if there is any difference, something stay there, or you leave more. And the general continuity equations shows that changes on flow in all directions, and this is the first order approximation of the continuity by this expression that here is a Taylor series that is only first order, is the same as the change in density. So if something, imagine you have people entering this box and you have a certain amount of people going out. If there is a difference, some people stays there. So now we have more density of people inside there, or less density if it's going, more people is going out. So imagine this is a wagon of metro or something like that, a subway. The other equation that is very important is the momentum equation, which is fundamentally the second law of Newton. So as you know, mass times acceleration, this is a vector. So we are talking here about the 3 dimensions. Is a water particle with certain mass as is going to be accelerated if we apply a certain number of forces. So just mathematically, we can express this as a total derivative of the velocity, and this is per unit mass of that water particle is going to be accelerated based on the summation of these forces, the applied forces. If we expand this total derivative, you get this super big expression here, which is the classical way of seeing the local and convective acceleration. This is called the total acceleration, or the advective component of the acceleration of the water particle. And this is the other classical way of expressing in fluid mechanics the forces, the summation of the forces that we have here. This is coming from this, again, this volume that is where we say, okay, there is a number of forces acting on the different surfaces. I don't know what is the origin of these forces yet. What I just know is that I have a pressure component, which is the pressure, the normal component that is acting in this surface, plus the shear forces that are acting on each of these faces, plus another force that has, and in this case, I'm just showing the x component of these equations. So there is another one for each of the y and c components in the 3 dimensions. No, so that was very fast. Hydrodynamics in 5 minutes or less. Maybe you are more familiar, you have seen the equations of motions that we saw before. The equation of continuity equal to 0, because when we have water that is fundamentally incompressible, then that change in density that term is not existing here. So we have here the continuity equation. So this is the other form, and this is another form of expressing the momentum equations where we have changed. This is already an assumption that we have changed these shear forces to these terms. This approximation is not true, it's a model. And this is what is called a closure model, because is needed because in these equations we have only 4 equations, continuity 1 and 3 momentum equations, and we have so many variables that we cannot solve this process. So we have to change those shear forces into an approximation. That is what we have here, the viscous shear, assuming that there is a relationship with the velocity and a parameter, which is the viscosity, the dynamic viscosity here. So this is the classical way of expressing, just for you, for maybe you recognize this. But why I care about all this and what I'm telling you this, because I want you to see where this expression from now in terms of similarity comes from. So this is again only the x component of the momentum equation. So we have here the advective acceleration, so local acceleration and convective accelerations that we can express in terms of 2 force per unit mass component, which is the force of local acceleration, which is this guy, plus the inertia force, that is these terms that you have here. And that is equal to a summation of different forces. And the classical forces that we know are around there is a gravitational force. So that's the weight of the water. Water is pretty heavy. So this is an important component. Viscous forces, so it is somehow, for example, the friction is involved there, and the internal friction of the water particle. Viscosity, imagine you have, instead of water, you have honey. This component is very big, so you have a lot of viscosity. And even though the weight is the same as the water, or very similar to the water, the viscosity is very important. So you won't be able to move very easily something like honey. We have another component, which is the surface tension. So what happens at the free surface? This is what happens with the elasticity of the water, which is a component that might be relevant in some cases. Pressure components. This is the pressure force that you may have in some cases. So you have a number of different forces. There are many others. Coriolis forces. There are electrical cohesive terms. Depends on the model you are dealing. And this is the reason why I said at the beginning, you have to understand what's going on, what are the underlying physics, because then you will know which of these forces are needed for your modeling. But let's assume that these are basically the most important one for the scale of the study that we are doing. And what just doing a little bit of mathematics, what I do is I bring the local acceleration on the other side, and I assume that I have all these forces. The same forces that I have here listed are here. And this is basically maybe taking into account 90% of all the forces that you will see in your models or wave energy converters or other devices. If I make these dimensionless, so I bring the inertia force dividing all these terms, I start having these series of terms that I have here. And if you think about it, you can start recognizing them. The gravitational over the inertia force is Fruth, is the Fruth number. The viscous over the inertia force is the Reynolds number. And these are less common terms when we have the when we're talking about the surface tension. Is called the Weber number. The elastic compression force over the inertia is the Cauchy-Mac. Is Cauchy or Mac is almost the inverse of the other. This is important, for example, when you have when you are doing studies of supersonic flow in airplanes, for example. This term is very important because of the air start to be the compressibility of the air. It start to be pretty relevant. Euler is the other dimensionless number that can be recognized between the pressure forces and the inertia, and this is called the Strouhal number. And in some cases is more or less important. But those dimensionless numbers, those fundamental numbers are, you probably recognize Fruth and Reynolds. Those are the classical. The others are less common. So just a little pause just for you to know how we define scale factors. And a scale factor is defined by simply a relationship between what we have in this particular value, x, in the prototype divided by the model. So in geometry, that is obvious. Your scale would be, I don't know, if you have something that is 100 meters long and in the model is 1 meter long, then your scale is 100. That is kind of easy. But that is not true for necessarily all of the, but sorry, this ratio is true for any variable that we have. So for example, the velocity, so the velocity in the prototype over the velocity in the model, that ratio still is the scale of the velocity, not the geometrical scale, but the scale of the velocity, the scale of the time, the scale of forces, whatever. We will see what are those numbers later on. And some important thing is that some of those scales are dependent of others. For example, the scale of the velocity, which would be the velocity in the prototype over the velocity in the model, as this definition, could be defined by the velocity this way in the prototype over the model. And if you do the math, turns out to be that the scale of the velocity is the geometrical scale. We don't put anything here, but just for convenience. So this is the geometrical scale, so the length scale over the time scale. And these define this. So if you know this guy or this guy, you know this guy because they are related. And that's how it works with all the other scales that we will see later on. So what is perfect similitude? Perfect similitude needs two things to happen. That all the summation of my forces in the prototype are this ratio of the same forces in the model is equal to 1. So this is the overall similitude. But at the same time, and that is the complication, is that individually the different forces are also the same between the prototype and the model. So the Fruth forces are these guys, so between the prototype and the model, Reynolds, and so on. And this is when we are entering in difficulties. And I'm gonna work around Fruth and Reynolds only. There is a similar thing that we can do for the others if it's necessary. For example, structural engineering is very interested on what's going on with Cauchy-Mac, for example, terms. But in our case, most of our cases are related to Fruth or Reynolds in terms of fluid dynamics. In electronics, mechanical, whatever, for example, happens in the PTO, there are other parameters that I am not super familiar with, but probably Ted Brecken could help us on that. So, for example, how do we derive the fruit? What is the meaning of fruit criteria? So, what is the fruit number? The fruit number is what we are saying is that, well, actually, this is the inverse of the fruit number, but what we saw before. Sorry, the gravitational of the inertia. Now we are gonna change it and we put it in the upside down. So the inertia could be expressed by simply the mass, and acceleration could be expressed this way. And the gravitational force is just mass times acceleration, gravity. If I work it out, these definitions, and this is just the definition of what is the acceleration and what is the mass, you end up in having an expression that probably you are very familiar with. So the square of the fruit number is the square of the velocity over the length scale, whatever it is, times g. So the classical term that you probably remember is that the square root of this number is the fruit number. So the velocity over the square of gh. So this is a velocity, could be whatever. This is the gravitational acceleration, and this is the water depth. And when I'm expressing here length, I'm talking about any length, any dimensions, geometrical dimensions that we are working. So this is the classical way of seeing the fruit number. And we see this fruit number in the prototype over the fruit number in the model is my fruit length scale. This is the length scale of fruit, if you like, as we defined before. If we start working out the numbers, turns out to be that if we have a fruit criteria, turns out to be that your fruit number, your scale of the fruit, is expressed this way. And then what happens? Well, this is the scale of the gravitational acceleration, and as long as we don't change the acceleration of the gravitational acceleration, so if we are doing experiments in this lab in comparison to what happens in any other place in the Earth, fundamentally this length scale is 1 because we are in the same gravitational field. You may laugh, but actually there are situations where this can be changed, and you put the model in a centrifuge, and by doing that you change the scale of this, and then that affects for a reason that you may be interested, not for when you are exceeding the limits of the similarity, you may want to change the gravitational force. The other option, of course, is going to the moon and then do the experiments over there if it's necessary. But normally, this is not what you're going to do. So if you go to a centrifuge, one of the largest centrifuges in the world is in UC Davis in California, and they go to 40 Gs. So they can change this scale by 40, and that affects my ratio of fruit number. But normally, this is not the case. And then when what we want is that the fruit number ratio is 1. So this length scale of the fruit number is 1. This is what we wanted to have as definition here. We want to have perfect similitude by doing these guys. So the ratio is 1. So when that happens, the length scale, sorry, the velocity scale is equal to the square root of the length scale. And that is a definition. This is how this comes from. And from here, we can start working out the relationship with the time. And probably you remember that the time scale in fruit models is the same as the square root of the length scale, and so on. There are a number of those that are that we will see later on. But this is the classical thing, and this is how this is coming from. This is by just the definition of the fruit number. Reynolds criteria. We do the same thing and basically define what are the inertia. This is the same term as before. We have the force related to the viscosity, which is defined in this way. And then by doing the ratio, we end up having the Reynolds number. The classical Reynolds number is expressed by the velocity times a length scale over the kinematic viscosity. So this is what makes Reynolds numbers typically super big, no? And a classical length scale that we use here could be the water depth, or this could be the diameter. For example, in pipelines, when you do analysis of water in pipelines, this is the classical UD over nu would be Reynolds number. So when you do this, turns out to be that you have this expression. So the scale of the Reynolds number is the scale of the velocity, the length scale, and the viscosity scale. So if we assume that the viscosity term, the scale of the viscosity is similar because we are using the same fluid. We may not use it. Sometimes people use it glycol. Some people have used alcohol for doing the testing to compensate for that. That is possible, but normally you don't. And if you work it out, if you want to have your Reynolds length scale to be 1, this implies that your velocity length scale is 1 over the geometrical length scale. And let me just go back and forth before. Through this, the velocity scale is the square root of the geometrical scale, and this is 1 over the length scale. Oh my God, they are not the same. And that is the problem. The problem is that you have a flow here that is described in a way, and you have a flow here that is described in a different way. So you cannot have a model that complies at the same time Reynolds and Fruth. And actually the same happens with the other numbers. So you have to do something about it. And the way of doing it is by playing around the process. So you are okay, or you assume that your the effect of the Reynolds number, for example, or the effect of the Fruth number is minimized in the model that you are reproducing. That's the secret. That's how you do that. Because, and this is why the perfect similitude is not possible. Never. The only way to get it the same is that you have full scale. So if this is 1 and this is 1, yes, we have the same length scale, and then Reynolds and Fruth is going to be the same. But that kills all the intention of doing reduced scale modeling, because then you have to build things full scale, and that is extremely expensive or impossible. Let's say we want to reproduce a tsunami in the lab at full scale. We cannot. So what we try to do is to go as big as possible to minimize those effects. If you keep working on the processes of the different numerical models, and this is just a summary of what I was just saying, that you cannot fulfill Fruth and Reynolds criteria, and how you can go around it. But I'm not going to stop there a long time, because there are a number of different ways of going around that. And I think it's more important for you to start seeing what are we going to do to solve these problems. No. So a little bit more on Reynolds numbers. So this is how the Reynolds is affecting, and which cases the Reynolds is affecting your numbers, and when you have to take that into account when you have when you are computing forces on structures, when you have friction forces or turbulent flow. You have to take into account those cases. So these are just plots showing that the drag coefficient, for example, in some models is described by the Reynolds number. What is interesting is that you see that certain cases, for example, here the friction coefficient, or here the drag force, above, for some conditions after certain size of Reynolds number, it becomes independent. So what we are doing is one of the ways of going around the problem of not being in compliance with Reynolds number, is that you move from, let's say, here to here. So we accept changing the Reynolds numbers because we know that the force, the friction factor, for example, remains constant. And that's how we go around it. We distort the model, and that is at the end of the day what we are going to try to do by running, for example, experiments where we change the roughness of the surfaces, when we change the flow, or we measure the flow previously, so we know that we can do that. If we cannot, then we have to do something else, and that's what I'm going to tell you a little bit later. So if you keep working with all these numbers, we talk about Fruth, Reynolds, Weber, Cauchy, and Strohal is not here, sorry. These are the condition, how you express in the most general form the scale factors for a number of different parameters. For example, the length scale is always the same. The velocity scale, you remember the velocity scale in Fruth was square root of L. It was 1 over geometrical scale. The Weber is the 1 over the square root of the geometrical scale, and in Cauchy the velocity has a scale of 1, and that is, the time is also very classical. You see the scale for the time and the velocity in Fruth models is the same, but in Reynolds numbers, Weber is not the same, and so on. So it changes depending on what you're doing, how you scale the acceleration, mass, and depending on the definition of each one, this is how you get these numbers. So this is a very complex table, but basically shows you everything you have to take into account in your scaling. What I have here is on one side is the most general form, and this is what happens when you assume that, well, typically things that you assume that your gravitational acceleration doesn't change or your fluid is the same. So that's how it's simplified, and that's how you get the classical numbers. But the most general form and expressing the scaling factors are what you see on the left. This is an example, and this is for you to have it later because the this presentation is being recorded, so you have information. But these are examples of what happens when I have in prototype a series of parameters. These are just examples. And what would you do assuming the simplified version, so the most common way of simplify your scaling, and what would be the classical numbers? So, for example, if I have a prototype, and this is only everything for a scale of 1 in 20, so you have a 10-meter whatever wave, for example, in your model in 1 in 20 is going to be a half a meter, and that is the same for the others. But your velocity is, let's assume, is 2 meters per second. Well, it turns out to be that in fluid is 0.45, but in Reynolds has to grow. This is if you are running a model respecting Reynolds at scale 1 in 20. If you want to represent 2 meters per second, you have to reproduce almost 40 meters per second in your model, and also increases, for example, in the Weber scaling. So that is the complexity that you have. Actually, you have to do the opposite in between fluid and Reynolds, for example, no, and so on. You have a number of different examples here. I think this table is probably better to take a look at. So what if you what would be the scaling of the different numbers if you have if you're comparing, if you're doing, for example, a model that is fruit, and is the fruit number is in a model that is scaled by fruit, well, the scaling is 1. But if you have a model that is scaled by fruit, the Reynolds number is affected with this scale, and so on. Weber number is going to be affected by this scale, and so on. So this is the model, and this is the parameters that we are scaling, and so on. So an example here, the same 1 in 20 scale, and we have, for example, in the prototype, a fruit number that is 0.2, which is classical subcritical flow. In the model should be 0.2, but the Reynolds in the prototype is 10 to the power of 7, but in the fruit number, the Reynolds number is going to be smaller. So that is how we change the Reynolds number in our if you are scaling based on fruit, and that reduction may or may not have a consequence in your results. So this is this comparison is telling you how if some, for example, Cauchy numbers are relevant. This is what you're doing to the Cauchy number if your model is only fruit. And you would ask, well, why or where do I have these situations? Well, this is a good example because we are starting a project when we are addressing this problem and is related to what you are in your field, which is the floating offshore wind turbine. So it's marine energy. And in marine energy, in floating offshore wind and also not floating, fixed offshore wind, we have the combination of waves and wind. And examples of offshore wind solution, floating offshore wind solution is what you see here. And for a number of years, there has been a number of different attempts to model this platform in the laboratory. This is a picture of an experiment that we did in Spain when I was working there a number of years ago. And here you see we have the wave machine. This is the basin, the wave machine here. So there's going to be waves later on. And this machine is a wind blower. This machine produces wind and is blowing wind into this on this platform. This is a physical representation of the waves and the wind. And as you know, this is not possible because we say that the waves, and I forgot to mention that waves and wave structure interaction from the hydrodynamic perspective are fundamentally governed by fluid numbers. So the gravitational and the inertial forces are the most dominant ones. When we are talking about wind, gravitational forces are not so important. The viscous forces are important. So the drag of the viscous forces in this platform over here are dominant in comparison to the gravitational. Why? Because wind is 1,000 times less heavy or lighter than water. So there is not such a relevant component in terms of gravitational force. So this is overcome by this incompatibility is overcome through a number of different experiments that was done here to compensate for that effect. So it was not Reynolds scale. It was the force was scaled properly, so we get whatever wind is necessary to produce the gravitational and the inertia force in this platform. But it's still incomplete. So what some people is doing right now is like the Norwegians or the French are intending to do wind by the effect of the wind, which is pulling strings. It's similar to what we did here with wind, but in this case, it's just the effect of the wind by pulling strings in different directions. So this has the problem of a constant flow that is unidirectional, and in this case, the French are trying to do something that is more sophisticated. How we do that? So and that has a dynamic response like what we don't have here. This is a steady flow. Here we have a way of changing the force of these pulling strings into the platform simulating the wind. And that is done through hybrid simulation. What you have here, this is a very short, compact way of saying what is hybrid simulation, which is a major field in structural engineering. So we have a model. Here, this is a representation of just a portion of the model. We have what is called the physical subassembly. The numerical subassembly is in a computer. So the orange element that you see here is what you see here. Only that part is being physically reproduced, but everything else is reproduced in the numerical model. And there is a number of ways of talking to each other. The numerical model is trying to reproduce. This is a classical dynamic motion equation of this bridge, and one part of that bridge, which is only this pile, is being measured and reproduced through physical modeling. What we are trying to do is do the same thing, and you see this is a more structural component. This is earthquake engineering. In the 70s, this has been done a number of times. What we are trying to do is to apply the same principles, but in here. So we introduce, instead of with strings, the wind forces that are computed through the numerical subassembly, is to introduce that with a robotic arm. So the robotic arm is going to be connected to the computer, and though that robotic arm is going to impose the forces that are produced by the wind in real time. That is the complex thing that we are doing, and I'm very excited that it's gonna. Hopefully, this is gonna happen somewhere at the end of this year. We're gonna be doing these experiments in the lab. Oops. And just to finalize and tell you a little bit of what are the laboratory effects in coastal studies particularly. So when we have to take into the differences between laboratory effects and scale effects. So when we have wave generation mechanism, what is the wave machine, how the wave machine is moving, that introduces a discrepancy between the reality and the so the prototype and the model. So that is a laboratory effect. If we have the right wave machine, then we have better waves. If we have the wave machine is introducing velocities that are not correct, then the wave is not going to be correct. So that is a laboratory effect. The theory of wave generation, are we using the right wave? So the video that you saw before is a solitary wave, and that represents a single wave that is breaking on an offshore wind pile. Are we using the right theory? Shall we use solitary waves, or shall we use frequency focusing waves? Shall we use periodic waves, and so on? boundaries is probably the most relevant component in laboratory effects. So you see here, this is not the ocean. I have a wall here that is only a portion that is introducing some effects, some frictions and so on into and the waves cannot go across this wall, cannot go across that wall, and the bottom is also fixed and is made of concrete. There is no sand, or there is no changes. We can put some sand trying to reproduce it, but most of the time we don't. And there is also at the bottom you have some friction and some effects on the flow. And this wave is going to go to the other side of the flume and is going to be dissipated. And that dissipation is imperfect, or is not necessarily the same as in the prototype. We don't have a beach. We don't necessarily have a beach because maybe the beach is 2 kilometers or 10 kilometers away from our model. So boundaries in that sense, so the wave dissipation and those walls and everything, or in the basin also, the walls on both sides are introducing laboratory effects. If we have a laboratory that is bigger or smaller or different shape of the right wave absorber, those the effects are going to be modified. It is true that the scaling may change. For example, if I have in my basin, in the basin here, we do a 1 in 1,000 model scale, then the effect of the walls is going to be minimized because we have more space. So in a way, the scale effects are being may control the size or are affected by the size of our facility. And then this may have a link, it's not the same, but may have a link with the scale effects and the laboratory effects. But of course, if you go to 1 in 1,000 scale, then you enter into a different problem with the scale effects of the other forces that we were seeing before. Measurements needs to be done. For example, here you see a number of different instruments and some that you don't see, and those are in the middle of the way. For example, here you see the canister of the ADB. This is something that is affecting the flow, and is part of the only way we have to install the ADB, the velocimeter, and then that is going to introduce other effects in the flow, which in prototype doesn't exist. Which instrument that you are selecting? You are selecting the right instrument to do the measurements. That is also a laboratory effect. If you choose wrongly, then you have a laboratory effect that has nothing to do with the scale effects. This place is very cold right now and is pretty humid and warm in the summer. This environment here is not the same as the prototype. Maybe we are doing some experiments that happens, for example, in Brazil, and when you try to reproduce Brazil here, it doesn't work. So those changes in temperature and climate inside of your laboratory is specific on the laboratory. We did some experiments in South Africa a number of years ago, and the heat was so high that people needed to enter the basin to stir up the stratification of hot water in the basin because it was affecting the measurements, and they have everything was open windows and everything, but still it was extremely hot, and that has some effects it was a laboratory effect that you don't see, for example, in the Netherlands. The water conductivity, we have that problem here. We use city water that comes with chlorine, and that affects the conductivity of the water, which is not similar to what we have in the prototype, which includes, if you like, the use of salt water or fresh water. We use fresh water, which has an effect on the density. We can compensate for that, but there is also a laboratory effect. In theory, we should be using, if we want to perfect similitude, we should be using seawater, which would be economically unfeasible, but it's not. And we are introducing a scale effect, but it's a laboratory effect in fact, because we could be using seawater. The reflection of the waves and how we absorb these waves that are coming back into this boundary is a little bit on the boundaries, but this is more dynamic. This is more passive. The opening of some of the doors around here, when we have a wind, that introduces wind drafts that are not realistic. So that's what I mean with these type of things. When we are doing floating studies, we need to keep the windows and doors closed because those are introducing some effects on the floating models. How long do you wait between two experiments? So the repeatability, this affects the repeatability and the conditions, the initial conditions of your model. So we want to have a cold start, which means everything is at 0, and we don't wait enough time. You still have something remains from the previous project, and that is a previous experiment, a previous trial, and that is a laboratory effect. You have to be patient in that case. How you generate the current, how you generate the wind. You saw previously a machine for creating wind. How we control the water level. Is it do we have too much leaks, or we have to reproduce the tides, and how to compensate for that. So those are just a series of examples, classical and most important examples of laboratory effects. And you see the differences between these and the scale effects that we saw before because of the scaling of the different forces affecting our fluid. And with this, I'm done. And let me finalize this. I wanted to have give you a little bit of time to answer some questions or anything that you are curious about. So Ted is asking that we are going to be wrong, always wrong in some way. And Matt mentioned that if there is an ability to determine different error values due to scaling. So those are related. And the first one is, yes, we are going to be wrong all the time. There is no way we are perfect. And the reason why is because we cannot reproduce all the different forces. What we know is the scale of those forces, the magnitude of those forces that we are doing wrong are small. And because we know it, then we know we are aware that whatever we are reproducing is not dominant in the process. But we know that we are going to be always wrong. That's true. It's imperfect. Whatever we do is physical or numerical, we are not going to be right. And that connection between the physical and the numerical is what is the answer to what Matt is mentioning, is a way of knowing. Remember, I said that the way of knowing how much is your scale effect would be to reproduce the same model in different scales and going even to the prototype. That is still done, and people is doing it. For example, in Belgium, now they are building a dike that is full scale and is only to measure the full scale overtopping on dikes. And that is going to be compared with the overtopping on dikes that has been done in small scale in the laboratory. So that's one way. The other way is running a numerical model that has the equations of motion, the CFD, full Navier-Stokes as best as we can. For example, OpenFOAM, that's one example. And we use that model to we validate it with the physical modeling reduced scale experiments. And if the assumption is that if our OpenFOAM is able to reproduce everything that happens physically in the lab, we can scale up the numerical model with the same conditions and assume that the physics are still the same because the model is reproducing this is doing the same physics. We can reproduce, we can check the values of whatever we are getting in full scale. So it's a full scale, but it's virtual, it's a simulation. And that is what most of the people is doing right now, is scaling up the numerical model based on the data that we get from physical modeling. The attempt of disappearing or removing all the laboratories in the world that happens in the 80s and 90s was because people thought that numerical modeling was taking over and that's the solution for the world. But they realized that those numerical models needs data, and then the booming of laboratories in coastal, particularly coastal laboratories in the world in 2000s, a little bit later than between 2000 and 2010, comes from the fact that those numerical models like OpenFOAM and so on needed validation and data. Geoff yeah, this seminar is going to be available. Is being recorded, and I'm going to send a copy of the presentation to Brenda so she can distribute that if you want to keep those slides as those are. We can distribute those for everyone, so you can have it. Other questions? Okay. I hope you learned a little bit on how we do and the things that we have to take into account in physical modeling.
This is Pedro. That was fantastic. It was really interesting. You know, I keep that spreadsheet, that presentation close by to always sort of refer back to it. So it's a valuable resource.